So Diophantine equation is one of the most classical thing, not important for only Olympiad mathematics. It is also very important in the sense of research mathematics. Okay, Diophantine equations are really a research part of number theory. Okay, no, but I'm not doing research, but Diophantine equation is my one of the research interest, and I have a goal to do research on Diophantine equations. So, all right. So as usually, I have set a problem sheet, and I have particularly categorized everything what you need to apply at which moment. I mean, what can be the big pictures. I have actually categorized this, and the thing is, you can. These are not only the methods. There are a lot of methods to do this. Okay. I'm sharing my screen. Can all of you see this? Or okay, great. Okay, great. So I have mainly take three part most probably. First part, this is the second part, and the last one is the fourth part. It's a modular arithmetic part, and another thing is that is called Fermat infinite descent part. Okay, and one second. So the thing is, these are not only four part. Actually, you can do any, means there are a lot of methods, but the thing is that for IOQM level or up to INMO level, I should say, these are actually sufficient. These are actually sufficient. Okay, these four category. And how to do that, I don't know. Okay, now I have done. Yeah, great. Now the thing is, you can see that most of the problems are taken from some national level maths Olympiad. Okay, so it also give you an idea that how to approach a problems in national Olympiad beyond your IOQM level. So that also help you. Okay, let's start the thing one by one. Yeah, all of you can see the blackboard. Okay. So before going to factorization, I think all of you know some basics thing, right? Basic thing in the sense, if I take a product A into B equal to some prime number, A into B is equal to some prime number, then A equal to 1 and P equal to B equal to some prime or something like that, right? And A equal to P or B equal to 1. I think all of you know this thing, right? Okay. And that's it. Another important thing, this is a thing. Another important thing is this, that maybe some algebraic manipulation, especially this is very helpful, x square minus y square. This is very important, like x minus y into x plus y. This identity is important. I know all of you know this from the past, but I'm just saying, for example, another identity may be a plus b plus c whole cube equal to, in general we doesn't remember the cubic formula, so I'm just doing it quickly, that a plus b whole cube, that is equal to a cube plus b cube plus c cube plus I think 3 into a plus b into b plus c into c plus a. This is the thing. Another important thing that is all required, that is, if a plus b plus c equal to 0, then a cube plus b cube plus c cube minus 3abc is nothing but or this part is not required even. It can be written as a plus b plus c into a square plus b square plus c square minus ab minus bc minus ca. This is an important thing. And the special case, a special case, when a plus b plus c equal to 0, then a cube plus b cube plus c cube equal to 3abc. Okay, these are the main thing. If we need to do some factor in yeah, okay, yeah, in this particular case we also can have a equal to b equal to something like that. Okay, great. And these are the important tool that we need for the first section, that is a factorization section. Okay, and as we progress, I'm going to give you rest of the thing. Okay, all right. So let's take the first problem and continue. No need to learn those Cardian methods or anything, okay, because those are just time waste. Okay, right. So this is the first problem. So how to factorize biquadratic and cubic equations? That can't be factorized in that way. Especially it's really difficult if you don't know the root of the cubic. So it's not possible in that way, and that doesn't require at all. If you, in some problem, if you really need to find out the root of cubic equation using some methods, you don't have any particular strategy, then remember that you are in a wrong way. Okay, because no such things required that I need to find out a root of cubic equation by Cardian methods or something like that. Okay, those are not required at all. Okay, so this is the first problem. This is the first problem. So when you see this type of problem, your first approach should be factorizing it. Okay, before going to any other method like looking into other modulo or jumping to the number theory or something like that, your first approach should be if you can factorize this particular thing or not. If you can directly factorize thing or not. So can anyone suggest me any factorization for this? Open bracket and factorized. Okay, let's do this thing. Very good. X square plus y square plus x square, right? Then y square plus 1. This is the first one. And for the second one, 2 into x minus y, okay, minus x square y plus xy square, that is equal to 4 plus 4xy. I can better write down the second part as, okay, x square y square plus x square plus y square plus 1 plus 2x minus 2y minus 2x square y plus 2xy square equal to 4 plus 4xy. That's my goal, that I need to make one particular side as a prime. So always remember that when you have a equation like this, always try to factorize it, and your goal should be to make one particular side as some prime number. And if we find out such thing, then we can actually apply this particular property, and that will be help us, right? Suggest me some factorization. It's simple. It's very simple to factorize. No, see, I can write down here xy. I can write down, so see, here is a x square y square. Okay. And here is x square y square, and here is a 4xy, something like this. Okay, here is a 4xy. So what can I do? I can bring it to this side, and then I can find out a 2 or something like that. Okay, so to find out a 2, and we can easily factorize it. We can find out a factorization 2. Please, someone asking for the control, please don't do that. It's really making problem. If you are not interested to do the class, just leave the class. Simple. Okay, please do not disturb others. All right. Yes, exactly. So here is a x, here is a xy, because here is a x square y square. Take -1 and take it square. Okay, xy -1, that's square, and then plus x minus y, that whole square. Maybe it's coming out, right? Yeah, here is a x and here is a y. Then we can take extra 2xy common, and this is just coming. Okay, that's the thing. And another thing. No, I wish not to make a whole cube, because in general first try to start with the square, right? If you go for cube, it will be a bit difficult to handle. Then I think it can be written as like this, minus, just observe that it can be written as this, into x minus y into xy minus 1, that equal to 4. Just check it, it can be written in this way. And now, can anyone say me what to do? Again, see that here is a perfect square formula. Okay, so what we can write it down? We can write it down is xy minus 1. Yes, exactly. Xy minus 1 minus x minus y, that whole square. Okay, this is basically equal to 4. Very good. So then it basically became that xy minus 1 minus x plus y. Now this is very easy to factorize, right? And someone suggesting me to make a one particular primes in one side. So this is the prime, plus minus 2. Right, now it can be easily factorized, right? It can be easily factorized. What will be the factor? As much I can remember, the factor is something like x, something like x plus 1 or y minus 1, somewhat like this. Yeah. Now this is basically equal to 2. No, check it. This will be the factorization. Okay, let me do this thing, that I'm taking, for example, suppose I'm taking y common. So it is what? If I take y common, it will be basically x plus 1. And if I take minus y common, this will be 1 plus x. So finally it gives this thing, right? That's it. Sorry, here should be plus minus 2. So now you can make it some case basing, like x plus 1 equal to minus 1, y minus 1 equal to 2, or x plus 1 equal to 2 minus 2, and x plus 1 y minus 1 equal to minus 1, something like this. And you can find out a lot of, yeah, some cases comes, and you can find out the thing. So this is a way. So one particular thing we find it out, that is that when you have a direct algebraic things like that, please do not go directly jump to the, yeah, you can write down the question on the chat. Okay, please never directly jump to any number theoretic approach. First try to factorize it, if you can factorize it or not. If you can factorize it, then it will be easy. It will be very easy for you to do. Clear? What is the formula for a cube plus b cube? You don't know what is the formula? This is the formula for a cube plus b cube. Oh, okay, okay. So these type of factorizations are important, and you can understand that you need a very good grip on algebraic manipulation to this type of problem. That's it. Let's take another problem. So this problem is from INMO. You can check it. Okay, this particular problem is from INMO. So the same thing. See, here is also algebraic things, right? Here is a direct algebraic things. So you can just, yeah, exactly. You can expand it. You expand it like this one. First we expand, then we again make some factor. So same thing here, we need to again expand it, then again we need to make some different factor, and obviously there is a 7 prime number, so I need to make a good thing so that 7 goes one particular side, and that gives us some cases, right? That gives us some cases. So I'm not going to that. Here even we have a problem from IMO. You can try this problem. Here we have a problem from IMO. Okay, I'm looking for the problem C. I'm looking for the problem C. Okay, here it is given that x, y, z are integers such that x cube plus y cube plus z cube equal to x plus y plus z equal to 3. You need to find out. No, not Newton sum. Newton sum do what? Newton sum basically raise the power from square, it's raised to cubic, cubic to fourth, like that, right? Exactly, we need to use this particular identity, what Saurabhi pointed out. We need to use this particular identity. Okay, let's take this problem and but are you sure that that is the unique pair? Remember a thing, for if you go for INMO level and if you just write down like solution like 1 1 1, this is the only solution without any explanation like this, you get 0. What is Newton sum? Newton sum I already explained on the polynomial class. You can look into the first recording, I think already uploaded in YouTube. You can check it. Yeah, Saurabhi. So exactly. So I already says that this thing x cube plus y, x plus y plus z, that whole cube formula, right? That is x cube plus y cube plus z cube plus 3 into x plus y, y plus z, and x plus z, right? This is the thing. Now do what? Now I know that x plus y plus z, that whole cube is basically equal to 3. Sorry, this thing is equal to 3. So it will be 3 cube, right? And what will be this? This will be also 3. So plus 3 into x plus y, y plus z, x plus z. Okay, now from here already it's coming out that x plus y into y plus z into x plus z equal to, so here it is 27, right? 27 minus 3 divided by 3, that is 8. Next, I can use the fact again that x plus y plus z equal to 3. So x plus y equal to basically 3 minus z. So here it is 3 minus z, 3 minus x, and 3 minus y equal to 8. Now we can factorize it again. We can factorize it. Okay, that's it. But you have to careful. You have to careful what? That the cube is actually equal to 1, because from this particular factorization you find out lot of terms where this particular condition actually get violated, right? Or maybe this condition violated. So you need to keep it in mind. So remember this thing, this kind of things sometimes given as a trap on Olympiad. I just apply the identity, I put the values, and I simplify it. Then I know that x plus y plus z equal to 3. Then I replace this x plus y, y plus z, and x plus z pairwise things by 1 by 1. That's it. Very simple one, right? This is the thing. It can reduce the large number of cases by using proper inequalities. Yes. If you, yes, that actually reduce. Exactly, Saurabh. Okay, so you can try this particular problem. I'm giving a hint for this particular problem. This problem may be difficult to some of you. Okay, for this particular problem, okay, for this is from IMO. This is from IMO. So you can do this thing that you can assume that this part as x, this part as y, and this part as z. Okay, so a minus 1 equal to x, b minus 1 equal to y, and c minus 1 equal to z. That is the thing. And from here you can find out the value of a, b, and c, right, in the terms of x, y, z. Just then plug it over here and normally divide it, you get a very good result. You can try, you should try this problem. That actually help you to understand what is the standard of IMO. And I'm saying that it is not very difficult. If you are a bit clever, then it will not be very difficult. It is simply doable. Okay. Otherwise, I know you are very pro people, you can find a solution in Google. Okay. Okay, this particular section is very important. This particular section is very important. All of you know inequalities, like basic inequality, like MGM inequality, Cosworth inequality, those things.
So in the previous class, we have done everything. All
Okay. That's great. Because we need the ideas of inequality over here. So I'm starting with this particular problem. This particular problem is from Putnam mathematics competition, I think 2003. Yes, it already has a look of AMHM. It already has a look of AMHM. So we can think for this particular question. Let's take it quickly. I will not waste much time on this particular question. This is fairly easy. I think this particular problem is from Putnam 2003. Okay, as already some of you pointed out, that is this thing, that k1 plus k2 plus so on up to kn, this particular thing into 1 by k1 plus so on up to 1 by kn, this is basically lesser than equal to n square, right? This is lesser than equal to n square, and I know that this particular thing is basically 5n minus 4, that is lesser than n square. So that means what? N square minus 5n plus 4 greater than equal to 0, right? Oops, sorry, yes, my bad. Otherwise the proper inequality never comes. Exactly. N square minus 5n plus 4 lesser than equal to 0. Now if you solve this, you find out what? One particular interval, like, yes, exactly, wavy curve method. So I think it can be factorized in this way: n minus 4 into n minus 1, that is lesser than equal to 0. So you find out that n basically lies in between 1 to 4. Okay, and you can plug the value of n and directly come up with a solution. You can directly come up with a solution, right? And you need to keep in mind that both simultaneously satisfy. This particular step followed by the AMHM inequality, you can say, or Cauchy-Schwarz inequality, you can say, this particular thing, like x1 plus x2 plus so on up to xn into 1 by x1 plus 1 by x2 plus so on up to 1 by xn is greater than equal to n square, if this is the inequality. Now it's very easy, right? Okay, that's great. Now try this one. Let's see what can we do with it. We have to find out all the solution for this equation. No solution. Why? I think you are comparing this particular problem with the past RMO problem, right? I think RMO 2017 or 18 contain this type of problem once. Yes, but no, this is slightly different. In that particular problem, the problem itself asks to prove that there is no such solution. I think 2017 RMO or 18. But here actually it has a solution. And this particular approach is one of my favorite approach. Here we have a very interesting concept, that is a proper bounding. See, no. See, the main concept is this, that we when we have this type of things like cube or square or any power, you can see this type of problem in several exam. Okay, when you have this type of things, you have to bound it between two consecutive things, or may not be two consecutive things, but if we can bound it between other two, like this type of stuff, x cube, and another thing, suppose I bound it between x plus k cube like this, so I can give the guarantee that the stuff that lies in middle, either will be x plus 1 cube, either will be x plus 1, or so on up to x plus k minus 1. That is the thing, right? And we need to use this idea. Okay, so whenever you have these type of things, that one particular side given as a perfect cube or perfect square or any perfect power, try to bound it. Okay, try to bound it by two perfect things. So first of all, we need to open this bracket. I need to open this bracket, but the thing is that I will not open this like a fool. I will open it very cleverly. And I am going to use some formula of summation, like I think everyone knows that summation of n cube means from n is varying from 1 to some number k, maybe. Okay, what is that? K into k plus 1 divided by 2, that whole square. Summation of n square from n equal to varying from 1 to k. What is this? What is this? K into k plus 1 into 2k plus 1 divided by 6. And I think everyone knows the summation of n equal to 1 to k of n, that is basically, that is basically nothing in but n into n plus 1 divided by 2, right? Yes. So I can simply open this bracket, right? So any general term of this equation actually look like what? X plus some k, that cube, where k is from 0 to n, 0 to 7. So I can, if I just open the bracket, x cube plus 3x square k plus 3x k square plus k cube, like this. If I take the sum, now it is very simple to take the sum, right? It is very simple to take the sum. Just take the sum from over k from 0 to 7. Get? I can easily take the sum from 0 to 7. And if you take the sum, finally you will come up with this particular thing. Obviously 8x cube plus 84 x square plus, here is a 3 and here is another x, so it will be 7 420x, I think, and last term will be very trivial, that will be 784. So if you just open this bracket, you find out this quantity. If you just simply open the bracket, you find out this. So what you get? You get 8x cube plus 84x square plus 420x plus 784 equal to y cube. This is the thing. So our problem basically reduced to this thing, that we need to make this particular stuff as a perfect cube. Means now what we need to do, we need to find out those values of x which makes it perfect square. sorry, perfect cube. Now here is a cube, but it can be generalized, right? We can take anything, square, cube, 4, anything like that. Yes, exactly. And x plus k cube. X plus k cube is simple. Just I open this particular x plus k cube in this formula like a plus b whole cube, and then I just apply this thing, that x cube plus summation. I take the summation basically, then I take the summation over k. I basically take the summation over k. That's it. Very good. So your y, what you find out, this particular quantity y, that cube basically lies in between. We have to find out two perfect good bound of it. Now what we get, we have this thing in our hand. We have this thing in our hand, and we can easily check that this particular thing is greater than 2x. Why I am taking 2x? Because it actually 2x cube. So this basically motivates us to take this thing, right? See, basically I have done nothing. I have just opened this bracket. So if you are not familiar with this thing, I don't know in which class you are in. So basically, if you are don't familiar with this thing, you can simplify this simple word. Okay. So then, and there is 784, and I know that this is obviously greater than 7 cube. So that's why I am taking this 7 cube. Okay. And another thing is that it is lesser than obviously 2x plus 10, that whole cube, right? That's it. So we get a very good bound for two things. That is y basically lies in between these two bound. So we find out that this y basically lies in 2x plus 7, that whole cube, into 2x plus 10, that whole cube. So what? Y basically lies in between 2x plus 7 to 2x plus 10. And what are the quantities lies in between 2x plus 7 to 2x plus 10? Only 2x plus 7, 2x plus 8, 2x plus 9, and 2x plus 10. These are the only possible values y can take, right? So I get the values. Possibly this inequality gets strict. You can check that this is strict inequality or not. Okay, I don't know. You can check it that this inequality is strict or not. Okay, is it possible that somehow I get equality? You can check it. Even if you check equality, no matter. Basically, if you take equality, finally you can't find out any solution. You over here you can't find out any solution. Now you have basically 4 values of y. More possibly it wouldn't be equal, because here is 7. Okay, 7 cube is obviously smaller than this thing. So this should be strict, but it actually doesn't matter. Yeah, the thing is that it increases the number of cases, but it doesn't leads you to a wrong solution. How I get 2x? Because I take the motivation of 2x, because this is the 2x cube, 2x whole cube. That's why I take 2x. I take this thing so that I take 2x plus 7 in such a way so that this is a good lower bound for the expression I have, actually this expression, right? I take a good lower bound, and similarly I choose a good upper bound, so that when why not 2x plus 8? You can check 2x plus 8. You can check 2x plus 8. Okay, and you also need to careful about these portions, because if it is too much large, this taking 2x plus 8, you can find out some problem. But 2x plus 7 is basically safe to take. No chance that it will be this particular thing actually smaller than this. So there is no such chance. Okay. So it is basically very safe. And similarly, this is also very safe thing to take. But 8 or 9, if I wish to make the restriction more perfect, then it will be a risk that I may miss something. So I wish not to do that thing. Okay. Means, yeah, obviously you have to make a good bound, but don't make the bound that much strict that you miss some solution. That will not be a good bound at all. So you have to careful about that. And now as you choose this thing, so you know that this particular quantity can be only this fourth thing, right? No, finally the thing is that y can be this particular thing. So you can find out the y cube, you can find out the y cube, and simply if you equate it, you get a quadratic in x. You get a quadratic in x, means y can take only this value, right? Y can only take the value 2x plus 7, 2x plus 8, 2x plus 9, and 2x plus 10. I think last two cases can be avoided, because this two case can be avoided because of the strictness of the inequality. You just need to check these two cases, and you can easily plug this value. You can check that 8x cancel out and it will become a quadratic. Then simple solve quadratic. Understood? You just need to solve quadratic directly and you get the final answer. Let me know if everyone got this step or not. This idea is very important, means this idea repeat in several of mathematics context. You can apply, no problem. Means you just need, you can apply, this is strict, no problem. That actually reduce the case. But if you make this thing equal, then it doesn't harm at all. Last step is this, that you just need to check this thing, that which one of this work. Means, for example, I choose y equal to this 2x plus 8. So I can expand y equal to 2x plus 8 like this, 2x plus 8, that cube, you can take it, right? So this will be some 8x squared plus blah blah blah, and you know that y cube equal to this, so you can plug this thing, 8x cube plus some blah blah blah. So simply 8x cube cancel out, and this will be a quadratic, this will be a quadratic, equate it, and you get a quadratic equation, right? And you can simply solve this quadratic. There are a lot of formulas to solve quadratic. That's it. I think Ashrith actually just upload this particular PDF in the description box on YouTube or something like that. But I will certainly provide the PDF, no problem. Another particular thing, that is this type problem. Okay. Another particular thing is this type problem, that when you need to solve this 1 by x plus 1 by y plus 1 by z equal to 3 by 5. How to proceed this type of problem? No, I never start teaching on YouTube. I don't have that much time. Okay. Exactly. We need to assume a good bound. But why I can assume this thing? Why I can assume this x is lesser than y or lesser than z or any kind of ordering? Yeah, when I can use the without loss of generality, why it doesn't lose any generality? Exactly, by the symmetry you can assume it, because the thing is that this particular thing is basically this is all symmetric in x, y and z. If you just change this thing x by y, y by z, z by x, you can check that nothing actually get affected in this particular problem. Means if you if you replace x by z and z by x, in the position you are not you are just changing this x and position of x and y. This side will never get affected at all. So I can assume that x is lesser than y and lesser than z. This is a very helpful thing. So remember a thing, you can't directly apply this thing. For example, if we go for this particular problem, not this one, maybe for this one, or this we can, this one, I can't directly apply that x is lesser than equal to y or something like that, because if we replace x and y, there can't be some changes, so it is obviously not possible, right? So but here we can assume that x one particular ordering in this variable, because if you have three number, you know that the number can be ordered in this way. That's the basic motivation behind it. So what finally we find it out? We find it out that without loss of generality, we can say x is greater than y greater than z. Yeah, exactly. Now I am taking the reciprocal of it. So 1 by x is lesser than 1 by y lesser than 1 by z. That's the thing, right? Then what can I do? I have this particular thing. I have this particular thing. So what can I do further? Not AMGM or AMHM, not like that. Yes, exactly. You can add this thing. You know that 1 by x is lesser than 1 by c. 1 by y, I think a good bound will be on x will be a good bound, right? Is lesser than equal to 1 by x. This thing. And if we sum it up, we know that this sum is equal to 3 by 5. So this is basically 3 by 5, which is greater than is equal to 3 by x. And that imply that 3 cancel out in simple word. That imply what? That x have to be greater than equal to 5. This side is not very helpful, because this side is helpful. No. X lesser than equal to 5 coming. How it's coming? If we add this thing, this is 3 by 5, and that is greater than equal to 3 by x. That means one by 5 is greater than 1 by x, and oh, okay, yes, that imply that x is basically lesser than equal to 5. My bad. Yes, means I am reciprocal. I am taking the reciprocal of the inequalities. Sorry. I am taking the reciprocal of the inequality. So this is a good bound. This is a good bound. But if I get the previous a bound like the previous one, like a like a lower bound of x, that is not very helpful, because the solution is asking for positive integer, and you know that you can't bound the positive integer above, but yes, you can bound the positive integer by below. Now you know what, Now you know that x is greater than 0 and lesser than equal to 5. So you can simply make some case basing, right? We can simply make some case basing. We can bound z, but the thing is that if we bound z, that will be a lower bound. Means, for example, if you find out z is greater than equal to, for example, I'm just saying 7, is it really helpful? Z greater than equal to 7, you get this thing, but how it help you at all? Yeah, it seemed like it is not going in a perfect way. Means, since we have another, wait, what, how this is possible? If 1 by x is lesser than 1 by 5, then obviously I think this should happen, right? Means x have to be greater than equal to 5. How can x lesser than 5? Means if I take x lesser than 5, then there is a problem that 1 by x is, means we know, right? If a lesser than b, then 1 by a is greater than 1 by b. So if x is lesser than 5, then 1 by x will be greater than 1 by 5. So how it's possible? So that's I'm saying that, sorry, this will be the correct one. Now it is not a good bound at all. It is not a good bound. Because x greater than 5 doesn't give any case. So this particular thing doesn't work. Now I can try to find out a bound on z. See, if we try the bound on z, so what we get finally, 1 by x is basically lesser than 1 by z, 1 by y is lesser than 1 by z, 1 by z is lesser than equal to, actually equal to 1 by z. Now add up. See, if you add it, then it will be 3 by 5, because this side sum up give you 3 by 5. This is lesser than 3 by z. Then it is giving z is lesser than 5. Now it is a good bound. It is a good bound. Right. It is a good bound because it gives you upper bound. So you can certainly say that z is basically greater than 0 and lesser than 5. So from here you can say that z equal to 0, 1, 2, 3, 4 and 5. Only these many possibilities are there. Z can't be 0, that's a different thing. But the thing is this. Now, I hope all of you can understand that why it is a very, I call this bound as a bad bound and why this is a good bound, right? Main idea is this. Okay, now which number is possible, which number is not, all of you can simply check it. That is not a very difficult thing. Now, obviously, you need to remove some cases. For example, z never can be 0. If z is 0, sorry, if z is 0, then this particular thing we can't define, this 1 by z term. So this can't possible, right? So 0 case removed. Similarly, you can check 1. If you check 1, it will be just 1. But if it is 1, then there is another problem, that 1 by x plus 1 by y plus 1 equal to 3 by 5. Now I know that this side is lesser than 1, but this side will be greater than 1. So again a contradiction. So this is again impossible. So only possibility is that you have 2, 3, 4 or 5. If we take 2, I think, okay, there is some problem. Maybe there is some problem. So suppose I'm taking that z equal to 3 maybe. So how to proceed further? If I take z equal to 3, what can I do? If I take z equal to 3, then observe that I get a particular Diophantine equation in two variable. Right? 3 by 5 minus 1 by 5. That is basically 2 by 5. And I hope this thing from here everyone can conclude that 1 by 2x plus 1 by 2y equal to 1 by 5. Right? And this is a very special type of equation. Like if we have some 1 by x plus 1 by y equal to 1 by n, I think everyone know how to solve it, right? Just take the LCM, multiply it. So it is xy, it is x plus y, it is equal to 1 by n. So that means it is just nx plus ny equal to xy. And then what to do? Then nx plus ny minus xy, and I need to subtract a minus n square maybe from both sides, and then we can simply again factorize it. It reduce a case of factorization. See, you can directly take x common from the first one, so it is basically n minus x, and you can again take y common from this one, from these two, so it will give you some y into, sorry, not y, you can take from this one, and this one I take this, oh sorry, not this one, my bad. I can take n common from here, so it is basically x minus n, and I can take y common from here, so it is again n minus x, that equal to minus n square, and again it can be factorized, right? N minus x into n minus y equal to n square or something like that. Maybe I'm wrong, some sign, maybe some mistake in sign, but the idea is this. Yeah. So from this step we can easily conclude this. Clear? Can I move to the next problem? Anyone have anything to ask from this one? You need to check the rest of the cases, okay? That if you find out something else, means I just directly jump to 5, you need to check that 3 or 4 works or not. 2, 3, 4. Okay, by the same method. By the same method, you need to check that 2, 3, 4 works or not. If you find out something. If you can't find out anything, then it's perfectly fine. So Semi, in this particular problem, 2a, okay, here you also can assume the ordering, right? Because here again, if you replace x by y and y by z, so doesn't matter, right? So here again you can particularly assume the ordering and you can do this. Okay, now I am going to the modular arithmetic method, and another method that's just an extension of this part, that is a Fermat infinite descent method. Actually, Fermat infinite descent method is a very long method. Okay, this is not this much. This is not only just this type problem. There are actually lot of problems. But the thing is that I'm not going to do much of this, because the reason is that that will be out of the stops. Okay, so that is the thing. Let's take the second problem. It's a very well-known problem. I hope already people know this. Okay. So here, okay, before moving to direct going to this point, I wish to figure out something. That is, those people are very very famous problem it is, and I wish to figure out something for those people are just very beginners in this field. That is, if you have linear equation like this, ax plus by equal to c, okay, this equation admit a solution if and only if the GCD of AB basically divide the number c, right? Yes, this is the thing. And I wish to say another technique of finding out modulo for higher powers. For example, when you have a x square, the helpful modulos are in general 3, 5, 7, 9, 11. These are really very helpful. 3, 5, 7, 9, 11. Okay. 6. Yeah, 4 is very helpful sometime for even odd case. Okay, now the question is that, for example, if I take the number 7, how to find out the, no, if you wish to go like that, in that way it never give finished. Okay, means even there is a problem in APMO where we need to take modulo 43. Okay, but I'm just talking about the basic cases for IOQM level. Okay, it never ends like that. Yeah, in APMO one particular problems comes like modulo 41 and modulo 43. You need to check that thing, but that is out of our goal. Okay, so x square, how to find out the what can be the residue or what can be the remainder when I divide a perfect square by 7? What is the method to do? I think most of you know, but still I'm just making a quick recap, that what are the remainder when we divide some number by 7? Exact 0 to 7, 0 to 6, right? 0, 1, 2, 3, 4, 5, 6. Yeah, 0 to minus 3 is enough, exactly. Because rest of the things comes by the negative remainder. Now we can just take the square of each number: 0 square, 1 square, 2 square, 3 square, 4 square, 5 square, and 6 square. Now this is 0, this is 1, this is 4, this is 9. 9 means what? 9 means 2. This is 16. 16 means again 2. 5 means 25, means 1. Oops, sorry. 25. So that means it will be 20. It will be again 4 because 4, yes, because 21, 25 minus 4. It is 36. That means again 1. So only possible remainders are 0, 1, 2, and 4. Similarly, we can do the rest of the things. We can check for 5, we can check for 9. This is the thing. Exactly. Now I'm getting to this particular problem. In this particular problem, we need to check modulo 7 from the both sides. We need to check modulo 7 in the both side. Now, if you take y factorial, means if you assume that y is basically greater than 7 or equal to 7, right? You can take the motivation of 7 just factorizing this to 2001. You can just take the motivation of taking this, because if you take 2001, you find out the remainder will be 2001. If you divide it by 7, what is this? Means what is this? If you take the divided by 7, what will be the remainder? -1, means 6 is a remainder actually. That means in the negative remainder term, it will be -1, right? So see that if you take modulo 7, then for y greater than equal to 7, the thing will be this thing, y factorial will be 0, but x square is congruent to -1 modulo 7. That is impossible. That is impossible, right? So what can I say? That I can say that y have to be lesser than equal to 7, and that gives a very easy solution. Means y equal to 7 means it is really thing, right? No, I assume that y greater than equal to 7, but next I can do this rest of the thing. So y greater than 0 and lesser than 7. Now you can take y equal to 0, 1, 2, 3, 4, 5, 6, 7. Sorry, equality will never occur. So only up to 6 it's sufficient. Up to 6 it's sufficient. Why it's impossible? Because if you take y greater than equal to 7, then y factorial is 0 modulo 7. Is 0 modulo 7, right? Because y factorial contain a term 7, so it is obviously divisible by 7. So I know that 2001 is basically gives a remainder -1 upon divide when I divide it by 7, right? So x square gives a -1. X square gives a -1 modulo 7. That is obviously impossible, because I know that a square number only gives this remainder 0, 1, 2, 4, right? So this is impossible. Same, it's clear or not? Actually, you need to look into the 5, okay, 6, 7, all these stuffs. Now you have means this is just for 2001. Even this particular number can be replaced by any other number like 2003 or something like that. It is possible to replace. Okay, even this IMO, sorry, not IMO, IOQM, they may be replaced by 2023 or maybe some other prime number. Okay, maybe some number, not prime number, maybe some number 22, 23, like that. Okay, so you need to check, means in this type of problem, you can say that there doesn't exist a solution in general on that way, that there may be a particular case where you can find out that there doesn't where doesn't exist any kind of solution. So you can do this thing. Okay, so you need to find out that particular number for which this actually get changed, this particularly get changed. So you can see that for y greater than equal to 7, this particular thing get changed, but the person who did the solution for first time, he obviously need to check it for the 0 1 2 all, not 0 2 3 all this modulo. Sir, do you have any idea how to solve 3 to the power a minus, even with the order and primitive root solution is? Yeah, how to solve 3 to the power a minus 5 to the power b equal to 2? I think this solution is quite famous one, right? This particular problem, 3 to the power a minus 5 to the power b. After the class, you mail me if you wish. Okay, I can check this thing. So it's just kind of Catalan conjecture, but it is quite related to Catalan conjecture. But it is quite related to Catalan conjecture. Means, if we take it difference 1, oh, your difference is 2, right? But in the case of 2, it also can be proved. In the case of 2, it also can be proved, I think. I have seen this solution before. Which solution? This one. See, basically, I have assumed that suppose y is greater than 7. Okay, first of all, obviously, in this type of problem, you know that in the problem, this type of problems, if you look into the last one or this one, our goal is basically to construct a good bound, right? And to construct a basically good bound, I basically take this thing. Okay, means I basically assume that y is greater than equal to 7, right? And if I take y greater than equal to 7, then I can find out that if we take modulo 7 from both sides, then there is a particular problem. That is y is basically lesser than means, then I find out that x square is basically congruent to -1 modulo 7, but it is impossible. Okay. I'm just taking one particular problem from Fermat infinite descent for the means just for this one, or maybe we can even even we can take this particular problem also. These two problems are from Fermat infinite descent, and the idea is very simple. Yes, it's very simple, very simple. Means those people who are in this Olympiad field for more than 1-2 months, they maybe know this solution. That's it. It's really very simple. But the thing is that I wish to point out something more. I wish to point out something more, that this particular problem can be developed in a different language. Like this particular problem can be stated like this. For example, if you divide both sides by z, if you divide both sides by z, maybe z to the cube, or in this particular problem, if you divide it by z square, whatever you like. If you divide it, so what you get? X cube by z cube plus 2 into y cube by z cube equal to 4. Now observe that this is nothing but two rational number, means you can assume that p cube plus 2 some q cube, that is equal to 4, right? This is the thing. So this particular problem can be stated in this way. Even this particular comes in several contexts in this way, that prove that on this particular curve there is no rational point. No rational point. Okay. This even you often observe this type of things, that x square by z square plus y square by z square equal to 3. Okay. And this means that if you assume this by capital X cube, capital X square plus capital Y square, this equal to 3. This means what? This particular problem, it can be stated like this, that on the circle of radius 3, on the taking center origin as a center, there is no point whose both coordinate are basically rational number, right? Those people are much interested in research mathematics. They knows that there is a branch in mathematics called elliptical curves and rational points on elliptical curves. In that case, we basically study this type of things. And there is another thing, I think everyone knows, this is a very famous problem, that x to the power n plus y to the power n equal to z to the power n doesn't have any particular solution in this thing. Okay, this is a very Fermat last problem. Yes, if you actually observe this particular problem, basically state this, that x by z that to the power n plus y by z that to the power n equal to 1, means in another word, p to the power n plus q to the power n equal to 1. This curve doesn't contain any rational number. Okay, that is the final thing. Andrew Wiles provider proves on elliptical curves. Yes, exactly. And he actually proved on these particular curves. Andrew Wiles proves. Okay, by the way, I'm just giving a solution for this particular problem because I know everyone knows the solution for this one, x cube plus 2y cube equal to 4z cube. How to proceed it? How to proceed it? And you just need to check the parity on the both side, right? You just need to check the parity on the both side. So the thing is x cube plus 2y cube equal to 4. This is the thing. Okay, this is the thing. And how to solve it? 4z cube. From here we can say, right, that this x is even number. We know that x is even number. And as x is even number, I can assume that x equal to some 2x1. X is some real number. So if I just put 2x1, that cube here, and this is basically 2y cube equal to 4z cube. That means it is basically 8x1 cube plus 2y cube equal to 4z cube. And I divide it again. So it is basically 4x1 cube plus y cube equal to 2z cube, like this. And again, if you proceed this way, then you can realize that y should be even. Okay, then you just take y equal to 2y1. In this way, you find out the solutions. You find out x is even, y is even, then you find out z is even. Okay, then entire equation basically turned into x1, y1 and z1. Again, you find out that x1, y1, z1 is even, right? So from there you find out another x2, y2, z2. But the thing is that this particular thing is basically getting smaller and smaller. Like x1 is the half of x, right? x2 is the half of x1, that is the half or 1/4 of x. x3 is the half of x2, that means 1/8 of x, and this continue if you just started to plug in. And this way you find out that it will be actually 0, because only solution is 0, because 0 is the only number that is infinitely many times divisible by some number. Otherwise we know that natural number set actually have a lower bound, so it's certainly stuck at a point, but sorry, it's actually have a lower bound, that is 1. So it is impossible until and unless it is 0. So that's the thing. Okay, so actually I take very easy problem today, not very difficult one. Because the thing is that for your IOQM level you really don't need to do very higher standard problem on on this particular Diophantine equation. Okay, and the thing is that, so that these 3 or 4 things that I teach, that is sufficient for your IOQM level. Even if you just learn this particular thing in a higher context, then it is enough for your, even for INMO level. Okay, no need to learn higher things beyond these 3 method. Yeah, there are another some approach like using the inductions, taking some other parameters. That's a different thing and not the thing. Okay, so that's it. That's it, guys. So I hope